I'd like to introduce you to unit number 3. Unit number 3, we're going to be looking at multi-dimensional motion. So up until this point, we've restricted ourselves to motion in a straight line. Whether it was a vertical straight line or a horizontal straight line, all the things we've done so far have been straight line motion problems. So today we want to introduce you to 2 or more dimensional motion. The big idea that you want to get down for this unit is the idea of independence of components. Independence of components is an idea that states that the y direction of motion and the x direction of motion can be treated separately. One more time, the x motion and the y motion can be treated separately. It's known as independence of components. So when we were doing our lab, we had 2 separate motions. We had the boat moving across the river, and we also had the boat moving down the river with the current from the river. 2 separate motions happening at the same time, and we're going to treat them separately. So what we'd like to consider is how are things going to change if we have a faster river. So the only thing we're going to change is the speed of the current, and we want to know how does that affect crossing time and how does it affect the amount that the boat drifts downstream. Then we're going to look at what happens if we have a faster boat. We'll keep the current in the river constant, and we want to find out how does a faster boat affect crossing time and drift distance. Okay, so let's start with a constant river speed. So let's take a look at what happens if we change the speed of the boat. Okay, so let's fire our boat across the river. As it moves across the river, it drifts with the same speed as the logs and the water. And it lands on the other side after 9.2 seconds. We're now going to double the speed of the boat. And we'll see now it gets across in about 4.7, and it drifts not nearly as much as it did the first time. When we plot these out, we find that we get an inverse relationship. So the faster we move the boat, the less time it takes to cross the river. And the less distance it will drift downstream. All right, so we have 2 inverse relationships. As boat speed goes up, crossing time and downstream drift both go down. This time we're going to have a constant boat speed, and we're going to change the current in our stream. Okay, so the first time we're going to have a river speed of 6. We're going to fire our boat across the river. We're going to monitor the time. We're going to monitor the drift. We see it takes 9.5 seconds, and it landed at about the 56 meter mark for downstream drift. Now we're going to lower our river speed to 3, wait for the log to pass, fire it, and we see it took exactly the same amount of time to cross the river, but we can see that the drift was half as much as it was before. So when we lowered the river speed, we made no change to the travel time. When we lowered the river speed, we lowered the amount of drift. It turns out to be a proportional relationship. So if we had doubled the river speed, it would have drifted twice as far. Okay, so the big idea with all of this is that when we do these problems, we treat them as 2 separate problems. We do an across the river problem and a down the river problem separately. So across the river refers to going across the river, and down the river refers to how far it's going to drift in the x direction. Since there's no acceleration going on, we can use our velocity equals displacement over time on both sides. I'm going to call the across the river y, simply because it's going in the y direction. And I'm going to call down the river delta x, because it's moving horizontally in this version of our program. Okay, when we deal with this, realize that you have to deal with triangles a little bit. Okay, so for instance, if our boat went 25 meters across the river and 30 meters down the river, and you wanted to get the actual travel distance, you would have to use Pythagorean's theorem. So again, the 25 is how far it traveled across the river, the 30 is how far it went down the river. The actual distance traveled by the boat would be the hypotenuse of that triangle that we just created. Okay, we can do the same thing with speed. So if we have the boat going 6 meters per second and the river going 4.25 meters per second, we can create a triangle out of speeds. Remember, when we give it direction, we call this now velocity. So we have 6 going in the y direction, 4.25 going in the x direction, and then we can find the actual speed of the boat by doing, once again, Pythagorean's theorem. So Pythagorean's theorem can work with both distances and it can work with speeds. Make sure all sides of the triangle are measuring the same unit, whether that is meters per second or just meters. Okay, if you need to get the angle of travel, it's a little trickier. Okay, so sometimes you need to know what's the angle here. So the way you're going to do this is with a trig function called tangent, which we will learn in a little more detail as we progress through the unit. But for now, it's going to be the side that is opposite the angle and the side that is adjacent to the angle. So that would be the 4.25 divided by the 6. You turn that into a decimal, and then to get the angle, you go on your calculator and you hit second tangent of whatever decimal you got when you divided these two numbers. If you get a strange looking answer, if it does not come out to be an angle that you're familiar with, your calculator is probably in radian mode. Make sure you switch it over to degree mode before you do this calculation. Again, we will be learning more about sines, cosines, and tangents as we progress. I just wanted to let you know now how you would find that launch angle. All right, when you did this, you should have gotten an hypotenuse of 7.35, and you should have gotten an angle of 54.7. Okay? And actually the 54.7 is the angle here, so you might have gotten the complement of the 54.7, which would have been 35.3. You can give either of the angles. You can either give it from the vertical or you could give it from the shoreline. Okay, so here's one I'd like you to try doing. Find the time to cross the river, find out how much you drift, find your total speed, find the angle, and find the total distance traveled. So again, you break it up into two totally separate problems. For a crossing time, that would be this side, the across the river. We would use the boat speed. We would use the distance to get across the river. And we would solve it for time. The key is once you get that time, you use that same time over here So that's time for answer 1. Then you use the river speed, and that will let you predict how far your boat is going to travel downstream. Okay, once you have how far it travels downstream, you also have the across the river. You should be able to find your hypotenuse. You should be able to find your angle based on what we talked about. For your velocity, you can do the 3.57 for the boat, the 4.24 for the river, and again you can find your hypotenuse to get your total velocity. Once again, you can also get your angle using the tangent like we talked about a moment ago. Okay, so that pretty much summarizes what we went through in class today. I have a practice problem online that you should try to make sure that you're able to go through this yourself and get the right answer. All right, good luck.